Ever feel that ground beneath you, kinda? Trembling? Get ready for a journey to a place where that feeling is real. The 2022 Menyuan earthquake site in Qinghai, China. And you know what? We're not just skimming the surface today.
Oh no, we're going deep.
Deep underground, uncovering the secrets this quake left behind. It's like earthquake archaeology.
It's amazing what scientists can learn from the aftermath. It's like piecing together a puzzle, but the clues are hidden deep within the earth.
Exactly, a giant detective story and our case file. A fascinating research article breaking down how scientists analyzed this quake after it happened.
And this wasn't just a little rumble. We're talking magnitude 6.9 on the Richter scale.
Whoa, okay, that's got to be huge. To put it in perspective, folks, that's about 10 times stronger than the 2016 earthquake that hit the same region.
And to make it even more interesting, this quake decided to happen right at the intersection of two major fault lines. The Lenglong Fault, or LLL, and the Tulaisian Fault, TLS for short. These faults, they're like massive cracks in the Earth's crust.
Okay, so picture this. Two enormous pieces of Earth's puzzle constantly pushing, grinding against each other at this very spot.
Exactly, and that pressure just builds and builds over time. Like imagine two hands pressing against each other. Something's got to give eventually. When it does, at these fault lines, well, that's when we get earthquakes.
A recipe for some serious seismic activity.
Absolutely. And one of the best ways to understand how these massive forces behave, studying the aftershocks.
Aftershocks, right. The little tremors after the main event. What makes them so important to scientists?
Okay, imagine you toss a pebble into a pond. You see the ripples spreading out.
Yeah.
Aftershocks are kind of like that. They give us a way to see how the earthquake's energy traveled underground.
So by studying those ripples, those aftershocks, scientists can trace the path of the earthquake itself.
You got it. In this case, they use this really cool technique called the double difference location method to map those aftershocks with incredible accuracy. Imagine trying to locate a firework, but just by the sound. You can kind of guess where it exploded, but
If you have multiple people listening from different spots, comparing how long it took the sound to reach them.
exactly, you can pinpoint that explosion much more precisely. And that's essentially what this method does with earthquake waves. It uses the tiny differences in arrival times at different monitoring stations to pinpoint where each aftershock originated.
That's seriously impressive. So what did they find? Were these aftershocks just randomly scattered, or was there a pattern?
That's where it gets really fascinating. They weren't random at all. They formed two very distinct clusters. An 18-kilometer segment to the west and a 13-kilometer segment to the east.
Two clusters and two fault lines. There's going to be a connection there, right?
You're absolutely right. It's like these aftershocks are breadcrumbs,
Yeah.
leading us right back to the source of the earthquake.
Okay, I like where this is going.
The western cluster lined up perfectly with the Tulaisian Fault. That's the TLS, remember?
Right.
And guess what? The eastern cluster lines up with the Lenglong Fault, the LLL.
Wow, so the aftershocks basically created a map of the faults that ruptured during the earthquake.
Precisely. But here's where it gets really interesting. The aftershocks also revealed something about how the earthquake actually moved. It seems the rupture. It likely started deep underground and then tore its way upwards.
Okay, so instead of a straight line, it was more like, what, a zipper unzipping from the depths.
That's a great way to put it. And this upward movement, that helps explain why there was so much damage at the surface.
Makes sense. Now, I've heard about this other thing called afterslip. You know how sometimes, even after an earthquake is over, things are still kind of shifting around?
Afterslip is fascinating. It's like a slow-motion earthquake where the fault continues to move for weeks, months, even years after the main event.
So the earth is still adjusting, letting out a sigh of relief even after that initial jolt.
Exactly. In this case, the scientists found evidence of afterslip happening along that western segment, the one associated with the Tulaisian Fault. They observed the aftershocks slowly migrating westward at a rate of about 4.5 kilometers per decade.
4.5 kilometers per decade. Incredibly slow, but still, it's happening. This means that even years after a major earthquake, the effects are still being felt. It's like the Earth's crust has a long memory. But what are the implications of that? Does it pose any risks?
That's a really important question. While afterslip itself isn't usually destructive, it can exacerbate other hazards. Imagine a hillside that's already unstable after an earthquake. That slow, creeping movement from afterslip, that could be enough to trigger a landslide.
So afterslip is like this subtle force that can have long-term consequences.
Precisely. And it highlights how important it is to consider these long-term effects when we assess the risks in earthquake-prone areas.
Okay, so we've zoomed in on this specific earthquake. What can this tell us about the region as a whole?
It underscores just how seismically active this area really is. We're
Yeah.
talking about two major fault lines constantly pushing against each other, each with its own history, its own movement.
So it's like a slow motion collision
Yeah.
happening right under our feet.
Yeah, in a way, that's a good way to put it. And this collision, it's been going on for millions of years, shaping the landscape we see today.
It's a constant reminder. The Earth, it's a dynamic, ever-changing system. And this research, it really gives us a front row seat to that action. By mapping those aftershocks, scientists are able to reconstruct the Menyuan earthquake in such detail.